This is Chapter 4, Applications of Differentiation, 4.1, Maximums and Minimum Values. First thing on here is extreme values, or extrema. We're going to go ahead and give that a star. Of f of x are the absolute maximum and min values of a function, singular is extremum. Let f of x be a function defined on domain D. We say f of c is the absolute minimum of f of x if f of c is less than or equal to f of x for all x values in the domain. The absolute minimum is the smallest y value over the entire domain. And note, we cannot use negative infinity, so this has to be an actual numerical value. We have the absolute maximum of f of x. This is if f of c is greater than or equal to f of x for all x values in the domain. Absolute maximum is the largest y value over the entire domain. And then again, cannot use positive infinity. They also call these global maximums and minimums, and these can occur at the endpoints. Down below this, I'm going to give the second box a star. Second box is local or relative extrema. Says let f of x be a function, then we say f of c is a local minimum if f of c is less than or equal to f of x on some open interval containing c. So you're going to look at the y values, and these are at all the valleys of the graph. Local maximum of f of x is going to be on some open interval containing c. You look for the y values at the peaks of the graph. So these cannot occur at endpoints. So make sure you know the difference between the wording of those two. Local extremas can happen at endpoints, cannot happen at endpoints on a closed interval, but absolute extrema can occur at endpoints. That's what we put up above. Notation, extrema are the y values and should be expressed as f of c equals b or as an ordered pair unless otherwise just asked for the x value in which the extreme occurs. And anytime you see extremum, we're talking about the maximum or the minimum. Extrema means both. So we have an example down below. And this says, given the graph of f of x and g of x below, identify any absolute extrema and any local extrema. So the first one that we have is a parabola opening down, and your absolute maximum is at the peak of that, which is at 2, 3. Your absolute min, because the graph continues on forever downwards, that's approaching negative infinity, and it's not a value, that's it. So we put none. Then your local max is also, in each interval, is also going to be that maximum value that we have there is 2, 3. And again, there is no local minimum because it does extend down to infinity. The second graph on part B, we have our absolute max. This time we have no absolute max because, again, both of those ends are pointing upwards, so none. For our absolute min, this is the lowest minimum value that we have. So the lowest minimum value that we have is down here, and it is 1, -3. Our local max, we don't have an absolute max, but local max is anywhere within any little intervals. And so we do have a peak on our graph, our maximum value at the graph, up at the top. And at that value, we have 2, 6. And then our local mins that we have are going to be 1, -3. And we actually have another value here, and that's going to be this point right here. So 4, 1. Okay, on page 2, it says not all functions have extreme values. So there's an example here. It says determine if the following functions have any absolute or local extreme values. So the first one has none. The reason why is because it's extending up to infinity and down to negative infinity. Likewise with B. And then C has no minimums, absolute or local minimums, because the graph is extending down to negative infinity. It also has no maximum value because this is undefined here. So this one is also an example of none. Next thing that we have is the extreme value theorem. I'm going to go ahead and give that a star. It's a theorem and it has a name, always important. So it says if f is continuous on a closed interval, so it has to be continuous on a closed interval from a to b, then f obtains an absolute maximum value and an absolute minimum value for some number c in that interval from a to b. So they could occur at the ends, and again remember global is the same as your absolute, or it could occur somewhere inside that graph between those a and b. So the first example here says find the extreme values from the graph of f of x below. Approximate when needed. So the first thing it's asking for is our extreme values. And so our extreme values here are going to be your absolute or global. So absolute or global, maximums and minimums. So we have an absolute max and an absolute min. So our absolute max on here is occurring at 9,3 at the endpoint, and our absolute min is occurring at 0, 0 at our other endpoint. Okay, so for our B, we need to find our absolute max and our absolute min. And so your absolute max is the highest of the highest, so the tallest point that we have, which would occur up here. And it looks like, say about say -1 comma -2.5 or positive 2.5. And then our absolute min, which is the lowest of the low that we have, which would be this endpoint down here. Looks like it's at 5, comma, we'll say -6.5. So again, you're estimating the best that you can. As long as it's reasonably close to that, it would make sense to have as an answer. On to page 3 at the top, it says Fermat's theorem. If f has a local maximum or minimum at c, then the derivative exists. Then f prime of c would equal 0. So if you have a local maximum or minimum at c, and if the derivative exists, then the derivative is equal to 0. So if you look here at the top of the graph, this would be our local maximum. And so we know that the derivative at this value, which is at -1, would equal 0. Since this is a maximum and the derivative exists there because it meets all those criteria. For our local min, we have a value down here at the bottom. And this local min, f prime of 1, is undefined. And this is because that's a sharp point. The derivative does not exist there. The next thing below, we have a critical value. Give that a star. So your critical values of a function is a number c is the domain of f such that either the derivative is equal to 0 or the derivative does not exist. So definitely something that we need to know. So big star there. If f has a local maximum or minimum at c, then c is a critical number of f. So we'll give that a star also. There's an example that kind of is discussed here. You guys can look at on your own if you have some time. So we have some steps down here to find critical values. Definitely something that we need to know. So to find a critical value, we set the derivative f prime of x equal to 0 and solve for x. Find the x values where the derivative is undefined by setting the denominator equation equal to 0. Be sure that the x values are in the domain of the original function f of x. So first example on here is f of x equals 3x squared minus 6x plus 4. It says to find the critical values for each of the following. So in order to do this, we need to take a derivative and set this equal to 0. So first, taking our derivative, we get 6x minus 6. I'm going to set this equal to 0. The graph of this function, this is just a polynomial, and our domain for this would be all real numbers. Solving this, we get x is equal to 1. So our critical value, and I'm going to abbreviate that CV, is equal to x is equal to 1. And there's no spots on this graph where we have anything that's undefined. So I'm going to put down f prime of x is never undefined. So our only critical value we have is at 1. The second one right next to this is g of x is equal to x to the 2/3. We're going to go ahead and take a derivative. And since we are dealing with a root here, the domain of this would have been all real numbers also. Taking our derivative, we'll have 2/3 x to the negative 1/3. I'm going to go ahead and rewrite this as 2 over 3 cube root of x. And this can never equal 0. There's no value I can substitute in there to equal 0. However, my derivative is undefined. When the denominator is equal to 0, so when I have 3 times the cube root of x is equal to 0, which is just going to solve out to being x is equal to 0. So my critical value is that x is equal to 0. Again, your critical values are found by either where